Hello, and welcome to this tutorial about writing numbers in the decimal, hexadecimal, and binary number systems. To aid our understanding, we will imagine that the place values of the various number systems are denominations of currency. We'll start with the decimal number system, the number system we use in our daily lives, and the one we are most familiar with. The place values in the base 10 or decimal number system are 1, 10, 100, 1000, and so on. We will confine ourselves to the first four place values in this tutorial. Since the place values increase by a power of 10, to represent them as denominations of currency, like the dollar for instance, the denominations would be the $1, the $10, the $100, and the $1,000 bills. Each denomination is 10 times the denomination before it. In the decimal number system, each place value is 10 times the one before it. They are based on powers of 10. Therefore, in our currency analogy here, each denomination is also 10 times the denomination before it, also based on powers of 10. As a result, the 2, the 5, the 20, and the $50 bills are excluded from our denominations because none of them represents a power of 10. So in order to implement our currency analogy effectively, we'll assume that the four denominations on the screen, each of which represents a power of 10, are the first four denominations of the dollar. The number we will write in all three number systems is 356. How do we achieve this? To answer this question, we will follow a practice generally employed by cashiers in real life when they give out change. What do cashiers usually do when they make change? They usually try to give you the fewest number of bills possible, and they achieve this by using the largest denominations they have available. So let us write down 356 in decimal by using the same principle a cashier would use. We'll start with the $1,000 bill. Will the cashier give you any $1,000 bills? No, because the amount of change is less than $1,000. Since $0,000 bills are given out, we'll write 0 under the thousands place. We now have this. We'll then proceed to the next denomination, the $100 bill. Will the cashier give you any $100 bills? Yes, because a $100 bill is smaller than the amount to be given out in change. But how many $100 bills would the cashier give you? The cashier would give you 3 $100 bills, because that is the most he or she can give you without exceeding the change amount. If the cashier gave you 4 $100 bills, that would exceed the amount of change due, which is 356. And if the cashier gave you fewer than 3 $100 bills, that would violate our objective of using the fewest bills possible. So you would therefore receive 3 $100 bills. Since we gave out 3 $100 bills, we will put down the number 3 in the hundreds place. Our decimal number is slowly taking shape, and it now looks like this. Since we have given out $300, how much is left to give out in change? To find out, we'll subtract the 300 we just gave out from the 356 total we have to give out in change. When we subtract 300 from 356, we get 56. So the amount of change remaining to give out is $56. We now proceed to the next smaller denomination, the $10 bill. Will the cashier give you any $10 bills? Yes, because a $10 bill is smaller than the remaining change amount of $56. How many $10 bills would the cashier give you without going over the amount left to give out? Out of the $56 remaining, the cashier can give you 5 $10 bills. He or she can't give you 6 $10 bills because that would exceed the amount of change left to give. And the cashier cannot give you less than 5 $10 bills because, again, that would violate our objective to give out the fewest total number of bills. So since the cashier will give you 5 $10 bills, we will write down 5 in the tens place. Our decimal number now looks like this. 5 $10 bills equals $50. Having given out this $50, how much change do we have left to give out? To find out, we subtract 50 from 56, which will give us 6. We have $6 left to give out in change. 6 singles or 6 units are obviously less than a $10 bill, a $100 bill, or a $1,000 bill. So we cannot use any of those denominations. And since this is the decimal number system, where numbers are arranged in sets of 10, any number smaller than 10, i.e. any number smaller than the number base itself, goes into the units column. Therefore, our remaining $6 are units, and they are placed in the units column. We have now completely written 356 as a decimal number, and it looks like this. Since trailing zeros are conventionally omitted when writing numbers, we'll eliminate the thousands place because it is not necessary when writing 356. And 356 can also be read as 3 hundreds, 5 tenths, and 6 units. Now on to the hexadecimal or base 16 number system. Of course, being familiar with the decimal number system and having dealt with it your entire life, the exercise we just performed in writing 356 in decimal probably strikes you as mundane. But I included it to give you a foundation that would aid you when writing numbers in less familiar number bases, like the base 16 or hexadecimal number system and the base 2 or binary number system. If you apply the same principle we just used to make change, you would find the task of writing numbers in base 16 and base 2 and any other number base much easier. We will write the same number 356 in base 16 and save my personal favorite, the binary number system, for last. Since we will be using the same principles we used in writing 356 in decimal, most of the explanations that follow will be self-explanatory. However, I will elaborate on any points I think are critical to understanding our exercise. Since the hexadecimal number system is based on the number 16, its place values increase by a factor of 16. To write 356 in this number base, we will still use the currency analogy, but this time the denominations will increase by a factor of 16. So imagine the dollar was based on base 16. The first 4 denominations of currency would be 1, 16, 256, and 4096, written like so. These are the first 4 place values of the hexadecimal number system. We would write them like this. You can see that the denominations are based on powers of 16. The first denomination, 1, is 16 raised to the power of 0. The second denomination, 16, is 16 raised to the power of 1. The third denomination, 256, is 16 raised to the power of 2. And the fourth denomination, 4096, is 16 raised to the power of 3. In the decimal number system, the headers H, T, U stand for hundreds, tens, and units. Here in the hexadecimal number system, the headers FTSU stand for 4096s, 256s, 16s, and units. The headers are plural. So how would we write 356 in the base 16 or hexadecimal number system? Using our analogy of making change, how would we give out $356 in change and, like a cashier would, use the fewest number of bills possible? As we did when writing the number in decimal, we'll start with the largest bill, the $4,096 bill. Will the cashier give you any of these bills? No, because the amount in change is less than $4,096. Since 0 $4,096 bills are given out, we'll write 0 under the header for the 4096 denomination. We now have this. We'll then go to the next smaller denomination in value, the $256 bill. Will the cashier give you any of these bills? Yes, because a $256 bill is smaller than the amount to be given out in change. How many $256 bills would the cashier give you? He or she would give you one $256 bill because that is the most he or she can give you without exceeding the change amount. If the cashier gave you two $256 bills, that would be $512. That would exceed the change amount of $356. Since we gave out only one $256 bill, we'll put down one in the 256th place. Our number will now look like this. Having given out $256, how much is left to give out in change? To find out, we'll subtract the $256 we just gave out from the amount we started out with, which is $356. Subtracting 256 from 356, we have 100. So the amount of change remaining to give out is $100. Now on to the next denomination, the $16 bill denomination. How many $16 bills can we get out of the remaining change amount of $100? We can get 6. 6 $16 bills add up to $96. So the cashier would give you 6 $16 bills. Our number would now look like this. Since the cashier just gave you 96 out of the $100 bills remaining in change, how much change is left? Easy to find out. We subtract the $96 from the $100 we had remaining. $100 minus $96 equals $4 left. Only $4 remain to give out in change. Now $4 or 4 units are less than 16. And since this is the hexadecimal or base 16 number system where numbers are arranged in sets of 16, any number smaller than 16, that is, any number smaller than the number base itself, goes into the units column. So the $4 are placed in a units column. We have now completely written 356 as a number in base 16, and it looks like this. Eliminating the 4096 place, which contains 0, we have. So in base 16, 356 is written as 1 256, 6 16ths, and 4 units. And now, onto my favorite number system of all, the binary number system. And as in the previous two number systems, we will use the analogy of a cashier giving out $356 in change using the fewest number of bills possible. Since the binary number system is based on the number 2, the place values increase by a power of 2. As you can see, the place values increase by a power of 2. Going from right to left, each place value is twice the one before it. The currency we are using has the same denominations as the place values. To avoid confusion, I will not be writing the place value headers in words like I did with the decimal and hexadecimal number systems. What makes the binary number system unique among number systems is that no place value can ever have a digit greater than 1. The highest digit possible in the binary number system is 1. 1 less than the number base, which is 2. In any number system, the maximum digit possible in any place value is 1 less than the number base. In the base 16 number system, the maximum digit possible is 15. In the base 10 number system, the maximum digit possible is 9. In the base 2 number system, the maximum digit possible is 1. And since no place value in the binary number system can have a digit greater than 1, in giving out our change, we don't need to determine how many of a particular denomination should be given out. It can only be 1. All we have to determine is whether a particular denomination is the largest denomination we can give out of the remaining change. Let's see this in action. We'll write the number 356 one last time, but this time using denominations that correspond to place values of the binary number system. As before, the objective is to make change using as few bills as possible. Can we get a $256 bill from the $356 in change? Absolutely yes, because $256 is less than 356. So the cashier will give you one $256 bill and we will place 1 in the 256th place. Our number now looks like this. We've given out one $256 bill in change. To find out how much we have left to give out in change, we subtract 256 from the amount of change we started out with, which was $356. Performing the subtraction gives us 100. We have $100 left to give out in change. So on to the next denomination, which is the $128 bill. Can we get a $128 bill out of the remaining change amount of $100? No, because the $128 bill is larger than the remaining change amount of $100. Since we are not giving out a $128 bill, we write 0 in the 128th place. Our number now looks like this. Next denomination is 64. Can we get a $64 bill out of the remaining change amount of $100? Yes, $64 is less than the remaining $100 in change. So the cashier will give you a $64 bill. Our binary number now looks like this. We'll subtract the $64 bill the cashier just gave out from the $100 in change we had remaining. That leaves us with $36 remaining in change. So let's go on to the next denomination, which is the $32 bill. Can we get a $32 bill out of the remaining $36 in change? Yes, a $32 bill is less than $36. The cashier will give you one $32 bill and we will place one in the 32 place. Our number will now look like this. After giving out that $32 bill, how much change do we have left to give out? Simple. Subtract 32 from the 36 we had remaining in change, and that will give us $4. We have $4 left to give out in change. On to the next denomination, 16. Can we get a $16 bill out of the $4 remaining in change? No, because 16 is larger than 4. And since no $16 bill is given out, we'll write 0 in the 16th place. No $8 bill is also given out because we cannot get an $8 bill out of $4 remaining in change. So we'll write 0 in the 8th place as well. Our number will now look like this. The next denomination is 4. Can we subtract 4 from the $4 remaining in change? Yes. So the cashier will give you a $4 bill, and we will place 1 in the 4 place. Updating our number, it now looks like this. When the last $4 bill was subtracted from the $4 remaining in change, the result was 0. That meant there was no change left to give out. And since all of the change has been accounted for, we will put 0 in the 2 and 1 place, since no $2 or $1 bill will be given out. We have now completely written 356 in binary, and it looks like this. This is how you write 356 in binary. And that will pull down the curtain on this tutorial. I hope this technique of using the analogy of making change to show how numbers are written in 3 number systems has been helpful. If you are still having trouble understanding the concept of number systems, you can watch my tutorial on the decimal number system, and hopefully you will find that helpful. I thank you for watching, and of course, like, comment, and subscribe, and stay well. Bye-bye.